We've seen it use matrices quite a bit. They're useful. An n by m matrix is basically a grid of numbers with n rows and m columns. It's common to see a matrix denoted as A equals Aij, where I is the row and j is the column. If A equals Aij and B equals Bij are two n by m matrices, then A plus B is the sum of each coordinate. If R is a scalar, Ra is the scalar times all the coordinates. As an example, if A equals 2, 1, 3, minus 1, 2, minus 5, B equals 0, 1, 2, 3, 4, 5, and C equals 1, 1, 2, 2, 3, 3, then A plus B is 2, 2, 5, 2, 6, 0. 3 times A is 6, 3, 9, minus 3, 6, minus 12, and A plus C is a problem. The dimension of these two matrices don't match, so we can't add them together. Addition and scalar multiplication are kinda easy, or they will be after you do it like once. Matrix multiplication is another beast. While it isn't exactly challenging, there are a few moving parts. Let A equal Aij be an n by m matrix, and B equal Bij be an m by k matrix. Then A times B will equal C, which is Cij, will be an n by k matrix with entries Cij equal to ai1 b1j plus ai2 b2j plus aim bmj. That's a little complicated and it probably doesn't make sense. We're going to do an example. But first, notice the dimensions of A, B, and C. The A is n by m and the B is m by k. The middle dimensions match, making C be n by k. And those middle dimensions always have to match for matrix multiplication to work. Let A equal 2, 1, minus 1, minus 1, 0, 3, and B equal 3, 0, 4, 3, 5, 4. Compute A times B. It's essentially row times column in a way. Take the first row of A and the first column of B. This will be the 1, 1 entry of C, or the upper left. Multiply the corresponding entries and add. I've written it very explicitly. Make sure you see where things are coming from. To get the 1, 2 entry, take the first row of A and the second column of B. Multiply and add in the same way. We've run out of columns of B, so go to the next row in A and repeat the process for the columns of B. The result is 5 minus 1, 12, 12. The only trick is to stay organized and try not to do everything in your head. I also usually use my hands to point out the row and column that I'm working on. It just helps me visualize what I'm doing. Here's an interesting example. Let A equal 1, 3, minus 1, 2, and B equal minus 1, 2, minus 3, 1. Take time to compute both AB and BA. I'll wait. I find AB equals minus 10, 5, minus 5, 0. And BA equals minus 3, 1, minus 4, minus 7. This should ring some alarm bells in your head. Matrices do not act like numbers. The order you multiply matrices is really important, and this example demonstrates that. In general, AB does not equal BA. You can also take powers of matrices. The only condition is they must be square. There are a couple of special matrices. First, the identity matrix. This is a square matrix with 1s on the diagonal and 0s elsewhere. The n by n identity matrix is denoted IN. You'll probably see why this is called the identity matrix on a homework. Probably. Next is the 0 matrix. This is the matrix with all entries equal to 0. The final thing I'll discuss here is the transpose of a matrix. If A is the matrix 1, 2, 3, 4, 5, 6, then A transpose, that's what this little t means, is 1, 4, 2, 5, 3, 6. The transpose basically flips the matrix. That's it. There are a couple of properties. First, A transpose transpose equals A. 2, A plus B transpose equals A transpose plus B transpose. 3, RA transpose equals R times A transpose. And finally, AB transpose equals B transpose A transpose. Be careful about the order on that last one. It's flipped. Another exciting linear algebra video. It was very hard in this video to not make constant jokes about the Matrix. It's a very, very good movie. If you haven't seen it, I highly recommend it. Kind of revolutionized action movies, invented bullet time. And I think I'm gonna go. Yeah, I think I'm gonna go keep watching it. You should probably do your homework though. After that, Matrix time.